Okay, so today we're going to look at Simscale. Now this is a finite element package. We're going to use it in class to do some finite element work with beams, but to learn how to use it, we're going to use some of the drawings we've already done in the past and do some stress analysis on those parts. So if you haven't done the drawings in the past, I'll put a link down below. You can click on that and go to the drawing we've done in the past. It's this drawing. So this part, it was part 5 I believe we did before, and I'm just going to prepare this for the stress analysis just by raising this head up slightly, just to give it an area to load onto. So if I go to sketch here, and then I'm going to pick that, and then construction, the outside, and then choose a circle that goes from the center, get rid of construction, and goes there. And now I'm going to extrude this, not a lot, by about 1/2 mil, so you can barely see it, but it is slightly raised. Simscale needs something discrete to put pressure against. It would put it against this whole surface unless we raised this up a little bit, so we just need to prepare it a little bit, but the rest of it is looking fine, so we can actually do a stress test on this. So Simscale, here's the package when you log in. It's very similar on its thinking to Onshape, that it's cloud-based, which is really good because Simscale, finite element analysis typically uses an awful lot of processor power, so you need quite a high-tech machine to run it. This all runs, the simulations run on their servers, and that means you can set a quite advanced simulation running and then get on with something else on your computer, and that simulation will be running on their server, and it'll drop you an email once it's done it. So if you're in an absolute mad rush for stuff, then maybe it's not quite for you, but it doesn't take too long to do the simulation. So I've logged in already. You'll need to set up a student account. It's very easy to do, non-profit account. It's, to be fair to Simscale, if you use the paid accounts, which are very affordable, they do simulate and run a lot faster than they do in the free, which you'd expect, that they put the priority to paying customers. But for a teaching tool and for you guys to learn how to use finite element analysis, you can't really go wrong with Simscale. They do a fantastic job, and it links really well with Onshape. So hit new project when you're into the dashboard, give it a title, my first FEA, it's a test run, we'll say it's manufacturing, we need to give it a, and we can put some tags in there. Tags are very useful later, especially if you've done hundreds of simulations and you can't remember where it is. If you put a tag, then it's searchable. It makes it a lot easier, but you don't have to put a tag in. So you've got a couple of choices here. You can either upload from your computer, or you'll see there's an Onshape button. This is the beauty of Simscale, that it interlinks with Onshape really well. And if you've linked it, I think if you've not done it before, the first time it asks you to link your Onshape account to your Simscale account. Okay, so it was part 5 I believe. It was that one, because it's got the little raised edge there. Import Now some of these things can take a few minutes. So what we're going to do in this video is stress test this. We're going to apply a force down on this boss at the top. We're going to look where the stresses are in this part, and then we're going to optimize it. We're going to make a few changes which should hopefully reduce the amount of stress that we get there. Okay, so that's gone in. It doesn't actually tell you when it's gone in. Don't keep hidden imports, otherwise it'll keep pushing loads of them in. Once that's done, you click the cross. Now the buttons work a bit differently. It's a left hold and drag to pan round, right does something different. So we've got our part. Now we're going to create a simulation. This is going to be a static test. We can do dynamic, we can do heat transfer, we can do frequency analysis where we can shove vibrations through. There's absolutely loads of different tests we can do, but for now we're just going to be doing a static load test. Create a simulation, and there we're into our console area where we can actually start doing some of this. It's really easy. It gets more complicated if you want to add more features and things to it, but for now let's just go with the basics of it. First of all, as we've described in class, you need to create a mesh. The way it works out the stress here is to calculate it over thousands of little elements in here, hence finite element. There's a finite number of elements in here, and we're going to analyze it. Now the more elements we can add, the more fine detail we're going to get about the stress, but the more elements we add, the longer the computing time is going to take and cost. So whether it's on your own computer running this, it'll cost computing time. You're going to need to have a more powerful computer. It'll take longer to run, and in business time is money. Or it's going to run on a server, which is going to be more expensive, and you pay for server time if you have the premium account here. So mesh is the first job, creating this tetrahedron mesh inside here, because with the process of meshing, we create tetrahedrons inside here. We can't use cubes because obviously they won't, when we've got rounded surfaces, it won't work. So tetrahedrons, if they're small enough, can form any shape we want to, roughly. So I'm going just for the standard for now. Sizing, we'll go for automatic, let it go, and we're going to run in the middle, firing course. Sometimes if you're running a model for the first time and you just want to see if it actually works, run on the course model. It'll run a lot faster. Make a few little adjustments to the model if you need to, then run it for the fine one later to get more detail. We're not going to run second order elements. 4 processors is fine. You can up it, but obviously that's going to cost more processor time. Okay, and generate. Now here we go. Core hours, you're given, I can't remember exactly how many, but we can look a little bit later, or I'll display it on the screen. You're given a certain number of core hours per year free by Simscale, and every time you run a simulation you use some of those hours. So eventually, if you run lots and lots of simulations, you're going to get to the point where you've run out of simulator hours. They are quite generous with the number of hours they give you, and of course that's core hours, not necessarily individual hours that it's running. And this is quite a processor intensive process. It can take a while to actually run this, so we'll just pause while it runs the meshing process. Okay, so that's complete. It took about 5 minutes. It's saying 0.1 of a core hour. Yeah, if you're sitting watching it, it seems to take for ages. What I'd advise is hit run on there, and if you've got some other assignment work to do, crack on with that in the background and then have a look at it. Otherwise it's a waste of your time sitting or watching it. Okay, so middle button can pan, left button you can look round. You can see it's a fairly coarse tetrahedron we're running here, mesh. So, and right click and push them back, zooms in and out. So next process is to assign a material to this. For the sake of this, we're going to go for aluminium. Now, one of the good things about the mesh is you can later on do a different material and do a different simulation without doing a different mesh. It can apply the same mesh to different materials. Okay, so this is the Young's modulus, 70 gigapascals, density, pass-on ratio for aluminium, which is how much it shrinks in compared to how much it stretches. We've gone through that in class, but just useful information, and this is how it's going to base the model on this information here. So we'll assign it to part 1 and go. Boundary conditions. Now we're going to have a few of these. So first one is the force pushing down. So we're going to create a force, and we're going to click on the surface that we want to apply the force to. Now we can see down here in the corner our axis that Z pushing up here, that's Z positive, and downwards is Z negative. Okay, so we're going to apply a force downwards, so that's in the Z negative direction, and we're going to apply minus 3000 newtons on that face. Then we're going to apply another boundary condition, because for what Simscale thinks now, it thinks it's sitting in free space. So if we apply the force down there, it just rotate round. We need to hold some constraint conditions about where it's being held. Now we're not going to do the best job of this. You could have multiple constraints here, but we're going to try and get this running simulated nice and quickly. We're going to put some fixed supports in, and those fixed supports are going to be these holes. We're going to imagine they're threaded, they're holding it, and it's just going to be pushing on that. In reality, we'd probably get some support from this area as well, but for now, just to get the effect of where the stress is going, we're just going to have the inside of these holes. Okay. Once that's done, we can actually run a simulation. I'm going to leave it set as run 1 because it is the first run. I'm going to hit start, and it's going to take some time to run. Now hopefully it won't take an awful lot of time to run on their server, because, well, to be honest, the tetrahedron is quite coarse, so it shouldn't be too many calculations. It's already up to 30%, and then we'll see the simulation results. So pause the video quickly, and then as soon as it's done, we'll return. Okay, so it finally finished. Took 5 minutes, 0.3 of a core hour to complete it. As you can see, it's not showing any results at the minute. We have to go into post-process results to do this. So go into post-process. There it is. We can move it around and see, but again, we don't see any results. So the way we can see the results is if we go to ISO volume, click a plus. Now we're change it from Crouchy stress to von Mises stress in both of these cases, and now we've got them all turned down to minimum. So if we turn it up, the maximum, we can see where the maximum stresses occur, and no surprise, it happens around these holes where it's being loaded, it's being pushed down, and it's applying force to there. If we rotate underneath, we'll see force being applied there as well. In fact, quite high forces. And then also underneath here, doesn't come as much of a surprise. There's quite a bit of force there in this corner. It's a bit of a stress raiser. We can see there. Now there's a few ways we can actually see inside where it is. it might be that we're actually just interested in where the stress is most. So what we can do there is, if we click back on the ISO volume here, not plus another one, and we remove some of the minimum stress areas, and we're left with just the maximum stress areas. Now we can see here that on this model the stress is big around these holes where we're applying a force, only on the edges, not so much in the middle of them. There's a lot of stress underneath here, there's a lot of stress on top, and a bit of stress around this top edge here where we've got these stress razors again, and as we go smaller we see. So if we were thinking of trying to optimize this in some way, not that it's a very realistic model, but we'd want to put more material where there's a lot of stress, and we'd want to get rid of material where there's no stress. Well, if we go back to here and we reduce the maximum now, we get rid of all those maximum bits, and what we're left with is the areas where there is very little or no stress. Now through the centre of that beam there doesn't appear to be much stress at all, so that would be a good area to start getting rid of material. Now we don't know, but there's probably a reason this rail's here, so that needs to stay, and this boss at the top, obviously that's there for a reason as well. But we could get rid of some material here and put some radiuses here and here and round here, which would decrease the stress and decrease the mass. So let's have a go at doing that.